Hello and welcome to another video. In this video we're going to be going over a number of ways to form target string given dictionary. And this one you're given a list of words and a target, and you need to form the target using the words under the rules. So target should be formed left from right, and you can pick a character of the words you're on, but basically once you pick that character you can no longer use that index or any previous index. So like let's say you're trying to make this B here for this ABA. I can actually make this bigger. Let's just go over this example down here. Yeah. So yeah, if you're trying to make like this character and you're saying I'm going to choose this second word and I'm going to choose this one, I can no longer use anything with this index or lower. So you're basically, the characters you pick have to be going left to right and you can't reuse something. And this is basically what they explained here. And then you repeat until you can form the target. So you can use also multiple characters from the same string and return the number of ways to do this to get the target, and then return it mod 10 plus 7. So they go over these examples. So essentially you can make ABA using this A, this B, and this A. So it'd be like this character, and this character. And actually, you can't have this example because these are the same index. So like you'd make the first A with index 0, this would be index 1. You can't do this, so you have to do this. So this is like one example, and then they go over a bunch of other ways to do it. And then here's example 2, same thing. So you can take the first character here, and then the second character here, and then the third character here, and so on and so on and so on. But let's just kind of simplify this problem first into you only have one word and you're trying to make a target. So let's just say, let's make an array here of, let's say we're trying to make ABA and we have something like ABB, something like this, right? And our target is ABA. So basically, the way this is going to work with one word, and same rules, right? So if I pick like this character, I can no longer use this index. I have to use characters after it. So basically what you're going to have here is you're going to have a pointer to the character you're making and where you are on the word. And this is going to be like a DP problem where essentially you're just saying, if the characters match, I have two choices. Choice 1, use the character. And choice 2, don't use it. And you can only use it if there is a match, right? So here, basically you can say like, okay, if this matches, and I'm just going to keep these indices in the DP, so essentially DP of like the word and DP of this target. All right, so this is the target. So if they match, I can move them both up, and then I can try the next thing. Or I could just be like, well, I'm not using this one. And then in that case, you keep the same character on the target and you keep using the word. And your base case here is pretty simple as well. So base case is just, you have two of them. One is done with target, or actually let's write it somewhere else. We can get rid of most of this too. And yeah, this word length is 1,000 and there's 1,000 characters in each word. Yeah, so you basically need something like, you can't really maintain more than just like the index you have or something like that. Essentially, right? Well, let me go back actually, because this is reasonably important. So 1,000 words, yeah. So you can't basically you can only maintain like in your DP you can maintain up to 2 states, either like the word you're on or the target character or something. But because each of these is 1,000, each state would be 1,000. So this can be like n squared. And in this situation, the simple problem, we would just maintain I, which is like what character we're on, and then J, what character we're on the target we're on. And then this has a constraint of 1,000, this has a constraint of 1,000, and that would be fine. So essentially, our base case is done with target, right? So we're out of bounds on the target, in which case that's a valid solution, so we can just return 1. And the second solution is we're done with the word, but we're not done with the target, which means we didn't make the target, so we just return 0, right? Like, if we chose not to use any character, for example, and we're still here, this would be a no solution, right? And this is really common in DP when you're trying to count all the number of ways you can do something. Basically, for a success, return a 1, for a failure, return 0. And this is recursive. So essentially, this is what would happen for one word, right? You basically say, like, if I use them both, then I move them both up. And if I don't use the character, then I stay on the same target, but then I move this up. And I can only use it when there's a match. Now, what happens when there's a bunch of these words? And to keep it simple, we can just say, let's just take this word and just make multiple. And move this up. So let's just say we have like 3 words. And that are the same. It's not really going to matter. So essentially then, we still have that same rule of if we use this index, we can't use this index later on or anything before. So we can still maintain this exact same index of like, and all the words are the same length. So we can say like I is the character of the word we're on. But now we're allowed to pick any of the characters and any of the words. So if there's a match of this character, we can go with this, or we can go with this, or we can go with this. And we want to be able to do this quickly because there could be 1,000 of these. So the way to do this is we can just pre-compute for every index the count of every character. So what this would look like is we would have another array. So basically we'd say like index 0, there are, store this in some way, there are 3 A's, and that's it. And then at index 1, there's 3 B's. And so on and so on and so on. So essentially, once we get to an index, we're going to check what character we're on for the target, and what's the count of this character that we have. And if this is a non-zero count, then there's that many ways of picking that character, right? Like if there's 3 A's, we can go with 1, 2, or 3. So the recursive is very similar, except instead of use the character if there's a match, just take count of character times the recursion. Right, so if this character does exist, that's how many choices we can have. And the recursion is still the same, where we just move the index up on both. So that's one recursive case. And then the second recursive case is we can just not use this index at all, right? And then in which case we just move this up. And everything else stays the same. So the problem is exactly the same. All we have to do is just for every index, pre-compute how many characters are there. And that's pretty easy, right? So for every word, we can just say like, basically for every index, we can maintain a dictionary or an array of like count of character at that index. And that the character will just be like A through Z character, because these aren't going to be all the same. So that's basically the problem, is you're essentially just pre-computing this, and then your recursive case is basically just the number of character you have times the recursive function, or don't use a character at all, which is just the recursive function where you only move up the index and you stay the same place in the target. And these base cases stay the same. So I think it's a lot easier to figure out like one word how this works. Yeah, that's basically it. So let's take a look at the code. And actually, I was able to do this one in Go, and then I added some comments and stuff to make it simpler. So essentially in Go, so I made a map. And you can do this one of 2 ways. This is really common. So whenever you use a cache in DP, you can either have an array cache or a dictionary cache. So like in Python, you can have like a tuple here. If you choose dictionary of like ij, if this is going to be your state. Or an array, you would just have like index I, index j. In Go, this is basically the same thing. You just make a type that's all your state for the cache that you need for the DP. And then I made the mod value, and then we just basically, so we pre-compute the counts. So at every index, we're going to have an array of 26 characters, and then we can just take the integer value of that character. So this is also really common in a bunch of languages. Essentially, you normalize your value. So if you take whatever character you're at, like let's say you're D and you do -a, A will have some ASCII value, so D minus A will be 4. Right, so basically that will make sure that the A is at index 0, the B is here, and so on and so on. You just take whatever character you're at minus A, because A should be 0. And so we just go through every word, we go through every character, and we add whatever that character is to the corresponding index in this counts nested array, which is going to be the counts of every character at every index. So basically, at every index, there will be an array of 26 values, and then an array of 26 values, and each of those values will represent the count of that character at that index. Then we can just make the cache. So I just made it outside of the DP, where the key is the tuple, which is like basically like a dictionary in Python. Same thing. So yeah, this is how you do it in Go. Or you could do the array, and then you return the DP. And so we can take a look at the DP. So the W is the length of the counts array, and also the length of the words. Actually, it's technically the length of one word because they're all the same length. And then T is the length of the target. And so if we manage to get to the target, we return 1 because that's a success. If we didn't get to the target, but we got to the end of the word, then we have no more characters to pick from. And also, I did this optimization where basically I just said, like, how many characters do we have left in the word and in the target? So for example, let's say here we have 3 characters left, where we're like over here. We don't have enough characters to continue. So if we don't have enough characters to continue, we can just return early. Because like even if we were to pick everything now, we wouldn't be able to make this. So that's just slight optimization there. If these get long, this will be like a lot better. Like imagine, these are like the word and the target are like 10 million or something. Or like let's say the characters you can pick from is like 10 million and 1, and the target's like 10 million. That means if you miss like 2 characters, you're done. So this would be like way faster than like going through the whole thing. And then the way you check if something is in the cache in Go is you just have this OK value. So you can basically get the value and OK. And if it's OK, that means you were able to get the value. So this is essentially whatever language you're using, just check if the value is in the cache. Then you set your result to 0, you get the character, and you get the count. And then if the count is greater than 0, that means we're actually able to pick this. So we're just going to take the count multiplied by the DP of the recursive state and mod it by the mod value. And if we want to skip this character, we can always do this operation. So we're just going to then keep the character we're at in the target the same and just increase the character we're at in the word. And then we just store it in the cache and then return. Yeah. So does this work? Pretty good. Yeah, I think I haven't tried this in Go enough, but probably if you use an array instead of a map in Go, it'd probably be faster. Same thing in Java, right? I was saying, like, if you're going to use a cache in Java, ideally you want to probably use an array because it's faster, less overhead. But that's just like small implementation details. Doesn't matter too much. But that's the main problem. So let's do the runtime and all that. Okay, so essentially we're going through every single word, and then we're going through every single character in every single word. So let's just say words is like how many words, and then W is like the length of the word. So that's going to be that to go through every single word to do this thing here. And then the DP, so I is going to be how many characters are in the word, and then J is going to be the length of the target. So this will just be like plus W, we said, was the number of characters in a word, and then T is the number of characters in the target. So this is this is how long the DP takes, this is how long it takes to go through every single character. And then space, so we do make the cache, which is, let's see, and then we make 2 things. We make the cache and we make this counts. So this counts is for every single character in the word, we have an array of 26. So that's just W, because 26 is constant. And then the cache is going to be the same as this guy. And that's really common in DP usually. And I think that is it. Yeah, I guess we can check here what this thing says. WT, oh, it probably copies what I have. Actually, oh, right, because W is smaller. So yeah, that's correct. Curious if I just get rid of this, what this says now. Let's find out. NM. Yeah, so this is basically NM, and this is these are like 2 different values, where this is like the target and this is the number of words, but basically NM kind of, because these are all 1,000 upper bound, so these would all be like 1,000 squared. And yeah, it's gonna be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. I think for shorter problems, I'll do like live coding, but for these longer ones, I think I prefer to just have like code written out, so it doesn't take like 30 minutes. And then if you don't like Go or something, you can just take this and GPT convert it to whatever language you want. So I don't think that's like a big problem anymore. So yeah, that's gonna be all for this one, and thanks for watching.